Hello and welcome to ECMath. Today, we're going to be looking at Precalculus section 2.5, which is all about breaking down polynomials using division. There are some prerequisites to this section. For it to really make sense for you, you've got to know what a polynomial is. That's section 2.3. You've got to be skilled with factoring. That's all the math classes up until now. You need to be familiar with complex numbers. That's section 2.1. And you should know synthetic division from section 2.4. If any of these things sound unfamiliar to you, I'd recommend going back to watch a previous video and then come back here when you're ready. So the first big idea of this section is something called the Factor Theorem. The Factor Theorem says that if p of x is a polynomial, we're going to use p of x instead of f of x for basically this entire section because we're always working with polynomials, but you can treat it like any other function. And c is a complex number, and remember again, complex numbers include all real numbers and all imaginary numbers and those things that are like combinations of both a plus bi. Then the following three things are roughly equivalent. One, which is c is a zero of p of x, and that's again real or imaginary zeros. X minus c is a factor of p, and to be a factor, x minus c will divide p with no remainder. So we have this idea of dividing with no remainder, zeros and factors, and they're all related. The zeros are also related to the x-intercepts, but only if they're real zeros. Imaginary zeros don't give you x-intercepts. So how is all this useful for finding zeros of polynomials? Well, let's take a look at this polynomial right here that we put together, and right away you'll notice that it doesn't really want to factor in any of the traditional ways. We could think about like grouping the first and last terms, but 31 and 70 really have nothing in common. There's not much that's going to group out here. So we need another way. So what we're going to do is effectively guess and check all possible zeros until we find some that work. And we're just going to start with 1. And so I'm going to use the factor theorem, and basically I'm going to divide by x minus 1 and see what the remainder is. And if I get a remainder 0, then I know that x minus 1 is a factor. To make this a little easier, we're going to use synthetic division. So here's that synthetic division set up. We have a 1 in the cage. That's because we're dividing by x minus 1. And then this 1 out here is because our leading coefficient on x to the third is negative 1, and all the other things are the coefficients of the polynomial that we're working with. So here's the division. And so we got 36 in this cell, which means that when we divided by x minus 1, the remainder was 36. And 36, last I checked, is not equal to 0. What that means is that x minus 1 is not a factor of this polynomial. So what the heck do we do here? Well, let's just cross 1 off the list and try the next biggest number. Let's try 2. So here's the synthetic division by 2. In reality, I would have kept all that scratch work. We're just kind of cleaning it up to keep everything on one page for the video. So with that synthetic division, we saw we got a remainder 0, which implies that x minus 2 is a factor. So we can start to write this thing as x minus 2 times something else. And the question is, what is that something else? Well, remember in synthetic division that everything that's not the remainder gives you the terms. This is the constant, this is the x squared. So really what we have been left with is x squared minus 2x minus 35. Now, we could take 1, negative 2, 35 and keep on dividing, but once you get down to a quadratic on something like this, not like that. Once you get down to a quadratic on something like this, it's actually best to just factor. And this one has 5 and 7 as factors, so let's factor that out real quick. It's minus 7 plus 5 because this guy is a minus 2 right here. And that means that the zeros, all three of them, are 2, 7, and negative 5 for this polynomial. Now, there's something I have to confess. This was a little bit of a cheat. I wrote this problem and I already knew what the zeros were. So I knew already that 1 wouldn't work, and I knew that 2 would work. I also could have, instead of using 2, I could have used 7 or -5 in there and gotten remainder 0. It would have been a different polynomial up here that we had to factor, but all 3 of those possibilities would have still yielded the same zeros. But what do you do if you don't know one of the zeros already? Well, then you use something called the rational root theorem. Now, this theorem looks a little scary at first, but it's really, really simple to use. So let p of x be a polynomial of the form a(n) x to the n plus all the way down to a1 x to the 1, and then a0, a constant term. We've seen this definition before. Don't get intimidated by the subscripts. It's just telling you that it's a polynomial in descending order of degree. The possible rational zeros of p of x are always guaranteed to be of the form positive and negative factors of the constant term, that's the term at the end, oh, not like that, the term at the end, divided by positive or negative factors of the leading term, the term at the front. There's a couple, subtleties to this. One, we're going to abbreviate possible rational zeros as PRZ, but once you start abbreviating, you lose the meaning of what P and R mean. We usually remember what Z means. So possible means that not every zero you get from this test or every possibility will actually be a zero. We're going to show you that in the example, that when we go back to the example we just did. And rational means that this only finds zeros that are rational numbers. Remember, rational numbers are things that can be written as fractions of integers. So we have rationals. This could tell you integer zeros, whole number zeros. But what it will never, ever tell you is if the polynomial had imaginary zeros or irrational zeros. So you still have to find those the hard way using the quadratic formula and factoring. But this test will help you break down the easy zeros so it's easier to find the hard zeros. So let's go and look at the previous problem. And I'm going to try to leave the test up here and maybe do my work over here. So we're saying, what are the possible rational zeros of this thing? Well, it's going to be, just following this form, factors of the constant term, which was 70, and divided by factors of the leading term. In this case, the leading coefficient was 1, so it's going to be factors of 1. But we do think about the factors of 1 as 1 or -1. So there are 2 factors of 1 in this case. And if there's other numbers out there, you just stick the other numbers in there with your PRZs. Now comes kind of the annoying part with this test. We're going to list out every possibility. So I'm just going to make a big fraction. On the bottom, I'm going to write plus or minus 1. On the top, I have to write every possible factor of 70. And I'm just going to stick a plus or minus at the whole front to remind me that every one of these could be positive or negative. So we have 1 and 70. I know we've got 2 and 35. We've got 10 and 7 make 70. And then maybe harder to find, if we take that 10 and divide it by 2, we could have a 5 and a 14. Oh, did I say 10 and 70? I meant 10 and 7. And then 5 and 14. So those are all our factors. And then it is actually really helpful to make just a list in numerical order of all of the factors. And so I'm going to do that now. You are allowed to list these with just a plus minus, like you could write this as plus minus 1. That's fine with me if you're just doing this for a quiz. But for the next step, it's actually kind of nice to have them listed out separately. And so that's what we're going to come to next. What do you do with these possible rational zeros? Well, we do something called zero hunting, or that I call zero hunting. It reminds me, if anything, of the old game Battleship, where you were just kind of guessing and trying to find hits based on your guesses. So the procedure roughly goes like this. We're going to list all the possible rational zeros. Then we're going to check each PRZ with synthetic, or I guess long division, going from small to large. And whenever we get something that works, and when we say works, it means it has remainder 0, we're going to reduce the polynomial down, write that 0 out, and eventually, every time we get a hit, we reduce the polynomial, eventually we'll get something that we can factor, and that will let us find the rest of the zeros. So we'd have just one example in this video, and here it is. We're going to find the zeros of this polynomial right here. So the first thing we have to do is list out the possible rational zeros. I'm going to make a list up here. Now I'm going to actually list those out, not in a fraction, because they all divide out by 1. So this is those 4. And those are the only numbers that I have to check with division. So I maximally only have to do 4 things to figure this out. Though I always recommend just start small. Like, don't start with 7, start with 1. Just everything works nicer with 1. So let's start with 1, set up some synthetic division, and start dividing. So we do get remainder 0 over here, which means that 1 worked. 1 was a factor. So since we got a remainder of 0, that means that x minus 1 is a factor. So just on the side, you don't actually have to do this, but for the purpose of the video, I'm going to. We can rewrite this polynomial as how it would be reduced to. So we saw x minus 1 is a factor, and then we can pull these coefficients to tell us what's left. So that's going to be an x cubed minus x squared minus 7x plus 7. Now, you could actually at this point sit here and maybe try to group this out and actually see some things that might group out, but I'm not going to do that. Let's just keep on doing the division because, you know, I don't feel like factoring, and maybe neither do you. So you might be tempted at this point to go to -1, but you can't, because it is always possible that in the fully factored version of this polynomial, the factor x minus 1 has an exponent of 2. And so because that's possible, we haven't ruled it out because we got a 0 remainder once, we need to check again. And when we check again, we're not going to go back to this guy, that list of numbers and coefficients. We're going to use the coefficients from the reduced version. And without even writing it out, we know the coefficients from the reduced version are those. So for the next synthetic division, I'm going to test 1 again, but I'm going to use these numbers. And that's really important. Your polynomial needs to get smaller every time you get a hit. Otherwise, you're never going to end. You have like a process that's not terminating. So to have this process ever just go to an answer, you got to make sure you're going smaller every time. So let's do the synthetic division. And we did, in fact, get a remainder 0 again. So that means that x equals 1 was a root not once, but twice. And so if we now write out the factored version again, I'm just going to kind of keep tracking that down here, it actually would be x minus 1 squared, and then all the coefficients that I'm going to pull out of here. So that's going to be x squared minus 7. Now, at this point, we could go check the remaining zeros. We could check, I guess we could check 1 again to make sure it's not repeated. We could check -1 again. We could check 7. We could check -7. But that's silly. To me, you're at a quadratic. Once you get down to where the remaining part has 3 terms like this, just write it out and try to factor it. And in this case, it does factor, but maybe not the way you expect. So what I might do is actually set this equal to 0, not like that, and then solve. So this gives us 2 zeros, and also we had the 0 of x equals 1. So here's our zeros. We'll rewrite those in a second, but this little solution also shows how this would factor. So if we were trying to factor this fully, it would be x minus 1 squared, and then x plus root 7, x minus root 7. And I wanted to stick something with square roots in there, because notice that these zeros were not on our list of possible rational zeros. That's because this test, like we said before, only finds the rational zeros, and root 7 is irrational. So there's no way that you would have guessed and checked root 7. You had to guess and check with the rational zeros until it reduced so you could find the irrational zeros. If these were imaginary zeros, it would be the same thing. You'd get some kind of quadratic. you'd solve it, and you'd find the answers are something, something with I. So how do we, there's a big mess on the page right here. How do we restate our answer? Well, let's just write out the zeros of P of x, even though I didn't really name it P of x, are x equals 1, root 7, and negative root 7. Just to put that all in one page. Because this work can often be difficult, you want to help your grader out by putting your zeros all in one spot somehow. That's the procedure. That's how you're going to do this. You list your possible rationals, you guess and guess and guess, and every time you reduce your polynomial down until it gets small enough that you can factor. Because these are problems that are meant to be solved by humans in a finite amount of time, usually the small numbers will work. That's why you should start small. Not always. Sometimes you have to try a couple things, but usually eventually 1 or -1 or 2 or -2 will work. And if you find that's not working and you're just hitting your head against the wall, maybe go back and check that you've got your division set up right and you've got your rational zeros listed out correctly. Because often these problems are solvable within a few steps just because we want them to be solved. So to close this video out, I just want to go through a couple tips. We'll keep it under 20 minutes. Tips for this zero guessing game. 1, you got to start guessing with small numbers. And don't forget your negatives. A lot of times people forget that -1 is the second best number to test after 1. And then positive and -2 are really good numbers to test if they are possible rational zeros. Another thing I see people do a lot is they'll do the division, they'll get a 0, and they won't reduce the thing down. They'll go back to the original polynomial and keep synthetic dividing. And the problem is they might find every 0 by guess and check, but they never make it smaller. And you'll never find the irrational or imaginary zeros unless you make it smaller every time. So you have to reduce your polynomial when you're dividing. That's the whole point of this. And if you're not doing that, kind of why are you doing it? And the other thing people forget is you got to check for those repeated roots. We had that repeated root of x minus 1, or repeated factor of x minus 1, repeated root of x equals 1 before. That's going to happen. From time to time, you got to check for it. Otherwise, again, you're going to get stuck. You're going to think, oh, I don't know how this factored. It's because you maybe didn't check for a repeated root. Finally, here are 2 important math facts. We'll zoom in on this one. Important math facts that help me when I'm doing zero hunting and when I think about these. So the first one is something called the fundamental theorem of algebra, or at least a version of it. And the theorem here says that a polynomial has no more complex zeros than its degree. The degree of the polynomial is a limit on the number of factors or zeros you can get. And if you think about reducing every time, that makes a lot of sense. If we have an x to the 6th and we divide it by an x, you're going to get an x to the 5th. You divide it by another x, you're going to get an x to the 4th. So by the time you divide it all down until you have x to the 1s all around, you better have 6 factors. The catch here, and why it's not exactly equal, is that sometimes roots are repeated. So the corollary here is that if you count roots with your multiplicities, the number of roots is always going to exactly equal the degree. Here's the example. We have a 6-degree polynomial that I wrote on a computer. I didn't actually multiply this thing out. And when you factor it out, it has 5 zeros. It has 3, 1 plus 3i, 1 minus 3i, root 5, and negative root 5. And this one would be really hard to do using the rational root theorem because of all those imaginary zeros. But we solved it on a computer, so it's already factored for us. And it has degree 6 and has 5 zeros, but the reason that happens is that our x minus 3 factor ended up squared. And so if you count that squared as 2, it kind of actually has 6 zeros, and the fundamental theorem of algebra adds up exactly. Here's another kind of corollary to that is very useful, I find. And it's that when you have imaginary zeros, they always come in pairs. Imaginary zeros always have a friend. That's because if you're going to have real numbers up here, you need to have an imaginary with its conjugate to make sure that there's no i's in the final multiplied out polynomial. So that's the second big idea. If you have one imaginary zero, they never appear alone. They always come in conjugate pairs. Here's a bunch of examples. Remember, imaginary zeros can be a plus bi. They can be pure imaginary, or they can even have things like square roots in them. You just still form the conjugate. All of those, when you multiply them out, give you a real valued quadratic, and that's why they must come in conjugate pairs. All right, folks, that's it. for this video. If you want more examples, there's another video on this channel that goes through a whole bunch more of these zero hunting. So I'll link that up in the description. And otherwise, the best thing you can do is do some problems, ask your teacher if you have any questions, and I'll see you all next time.